Good morning, my dear students. Now we are going to talk about radius ratio. What is the radius ratio? Radius ratio. The structure of an ionic compound depends upon the stoichiometry and the size of the ions. Listen. First one, the structure of an ionic compound. Listen carefully. The structure of an ionic compound depends upon. Listen. The structure of an ionic compound depends upon the stoichiometry and the size of the ions. Listen, depends upon the stoichiometry and the size of the ions. Generally, the ionic crystals, the bigger anions, are present in the close CPA, or CPA means close packed arrangement. Listen carefully. In ionic crystal, the bigger anions, because gain anions means gain of electrons. Therefore, bigger anions are present in the close packed arrangements. The bigger anions present in close packed arrangements, and the cations occupy the voids. Listen, the cation occupies the voids. Listen first again, listen carefully. The structure of an ionic compounds depends upon the stoichiometry and the size of the ions. Generally, the ionic crystals, the bigger anions, are present in the closed packed arrangements, and the cations occupy the voids. The ratio of radius of cations and anions, RC plus means radius of cations, right? RA minus means radius of anions. RC plus radius of cation, RA minus radius of anion. RC plus RA minus loss of one electron, the smaller size, gain of one electron, large size. Okay, the structure of ionic compound. Listen, the structure of ionic compound depends upon the stoichiometry and the size of the ions. Generally, the ionic crystals, the bigger anions are present in the close packed arrangements, and the cations occupy the voids. The ratio of radius of cation and anion, RC plus divided by RA minus. Listen, plays the important role in determining the structure. Very important. The plays the important role in determining the structure. Listen, first one, radius RC plus divided by RA minus, and coordination number and structure and example. Okay, structure coordination number 3, 1 2 3. B means anions, bigger anions, H cations, smaller size. Coordination number 3, structure trigonal planar. For example, BH3 or B2O3, BH3 or B2O5. So radius ratio, the trigonal planar radius ratio 0.155 to 0.225. Next one, tetrahedral. Is a tetrahedral. The tetrahedral coordination number 4. Example, CH4 or ZNS. Radius ratio of the tetrahedral 0.225 to 0.414. and molecular geometry octahedral. Next one, octahedral. Sorry, octahedral. Octahedral coordination number 6. Octahedral coordination number 6. 3, 4, 5, 6. Okay. For example, NaCl or SF6, etc. or IF6, etc. Radius ratio 0.414 to 0.732. And another one cubic. Cubic. CUPIC. Another one cubic. Cubic at coordination number 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. For example, CSCl or NaCl. Values 0.732 to 1.0. Next one, Scott-T defect. It's a very important defect. Point defect. 4 types of defect: point defect, line defect, interfacial defect, and impurity defect. Okay, the point defect classified 3 types. First one, Scott-T defect divided by classified 3 types: non-terminal defects, preliminary defects, and impurity defects. Okay, the terminal defect 2 types: Scott-T defect and Frankel defect. Okay, first one, Scott-T defect. Definition: Scott-T defect, very important 3-mark question. Picture and definition. Scott-T defect is a type of point defect. Listen, very important, type of point defect or imperfection in solids. Scott-T defect is a type of point defect or imperfection in solid which is caused by a vacant position that is generated in a crystal lattice. Which is caused by a vacant position that is generated in a crystal lattice due to the atoms or ions moving out from the interior to the surface of the crystal. Listen, Scott-T defect is a type of point defect or imperfection in solids which is caused by a vacant position that is generated in a crystal lattice due to the atoms or ions moving out from the interior to the surface of the crystal. Next important one, Frankel defect. Frankel defect. When an atom or smaller ion leaves its place in the lattice. When an atom or smaller ion leaves its place in the lattice, creating a vacancy and becomes an interstitial by lodging in a nearby location. Listen, creating a vacancy and becomes an interstitial by lodging in a nearby location. Okay, Ag plus is missing, but that Ag plus move to interfacial position. The Ag plus missing, but in the Ag plus move to Ag plus in interstitial position. Thus, a vacancy is created in the lattice. The type of defect is called Frankel defect. Listen, when an atom or smaller ion leaves its place in the lattice, only cation. When atom or smaller ion means only cation leave the space in the lattice, creating vacancy and becomes an interstitial by lodging in a nearby location. Thus, a vacancy is created in the lattice. This type of defect is called Frankel defect. Next one, metal excess defect. What is a metal excess defect? Very simple. It is a defect in the ionic solids where deviation from the usual structure is occurred due to the absence of the metallic ion from the two lattice points.